Hello everyone, welcome to another video on shell coding on the ARM Assembly Linux 32-bit course presented on YouTube. So in this video we are going to debug our program which we have created in previous video. So for debugging purposes we need to install a utility known as GDB. If you are on any kind of ARM device like Raspberry Pi or any ARM device with a Cortex Profile A processor, then you can just simply install using sudo apt install GDB. Although some operating systems have pre-installed GDB, but still if you have not, you can just download it using sudo apt install GDB. But if you are on any kind of non-ARM device and created your ARM binary on any Intel based processor, then you have to install a new kind of debugger. It is also from GDB, but it is known as GDB multi-arch. So what is the difference between a native GDB and GDB multi-arch? So I will just show you in the computer screen what is the main difference, what we will see in a normal GDB and this GDB multi-arch. So let's move to the computer screen and debug our HELLOWORLD.s ARM assembly program. So let me just show you the architecture of my device. It is using x86-64 architecture, or we can easily say Intel architecture. So the normal GDB will only be able to just debug the x86-64 binaries or Intel assembly binaries, which we can identify by just viewing the architecture that the GDB supports. And all the architecture that our GDB supports is i386, i386 Intel, i386 and all of the stuff, including the i8086. So all of these are Intel assembly format. That's why the normal GDB of the Intel architecture supports only Intel assembly instructions. So what does GDB multi-arch is different from the normal GDB? It supports more than 200 plus architectures of assembly language, or we can say more than 200 types of binaries we can debug using GDB multi-arch. Let me show you. So see, there are totally 200 possibilities, more than 200 possibilities, including the MIPS assembly language, Spark assembly, M68 assembly. I think M68 is not used nowadays. i386, which is the common thing in normal GDB. ARM 64-bit assembly, ARM version 3 or legacy assembly, ARM64 or the 64-bit assembly, MIPS assembly, and many other things. So every assembly language which have ever used by any program, by any binary, can be debugged by the GDB multi-arch. So upon closing all the terminals, let's debug our Hello World program. So upon viewing the HelloWorld.s file which we have created in our previous video, so we have declared a string hello world with the ASCII directive, declaring that the string is null terminated, declared an entry point where we have just used the write syscall to write the string to the output, to the terminal output, and gracefully exited the process. So for debugging purposes we had to use a utility we have installed from the initial setup video of the fourth video of the playlist, the QEMU. So by this using the QEMU arm, using tag L to explicitly just link our binary to a shared library which is stored in user ARM Linux GNU EAVIHF, using the tag G to create a debugger server, GDB server, on a port 1234 of the process hello world which we are going to debug. So what does this G do is create a localhost server into our machine, by which we can just access our debugger session remotely. So after entering, we can see that a server is created on port 1233, which we had just described after creating 1233. 1234 was in use earlier, so sorry for that. So how to just access the debugger session of the QEMU ARM process, debugger server process? So we can use something called file hello world to just import all the symbols used in the file or the executable. Then use target remote localhost 1233 to just connect to the debugger session active remotely. So from there we can easily get the session of the debugger session of this process. What we can see here in the output, we can see that all the instructions we have just declared in our file is just displayed here. Let me show you. So like move R7 with 4, move R7 with 4, and all the instructions that we have declared in the underscore start function are declared here. Upon just entering SI or step instruction, the instruction is one instruction is skipped or processed. So after looking at the value at R7, we can easily see the value is 04. So from this instruction we can easily say the value at R0 will be 1. First look at the value at R0, it is 0. After this instruction, the value at R0 will be 1. So after looking at this instruction and comparing it to the file we have created, there is a slight difference which we can see that there is a declared string hello world variable, but here is something called relative addressing method or PC, #16. So what does the assembler do at base level is the assembler cannot understand the variable names. It can only identify the memory addresses, not the variable names. So the PC, #16 is actually the memory address located here, somewhat here. So it uses some technique called PC relative addressing. And after stepping one instruction, the value at R1 will be the memory address of the string hello world variable. So it is 20098. If we check the memory address of the variable, it is exactly the same. So as I say, assembler uses a technique called PC relative addressing, by which it may just refer to the memory address of the variable which we have described in our program. After stepping one instruction ahead, before that we can see a difference, a change in our debugger result. Like in program we have used the load instruction where R2 is stored with the memory address of the length, but in the debugger output the instruction is changed. Instead of using the load register, the move instruction is used. So this is because the debugger analyzes that this instruction is not loading any kind of instruction into the R2, it is storing a value directly. So it dynamically changes the instructions and change load register to move instruction and R2 with 11. So this is used to just lower the execution time or to make the debugger output simpler. Let's just step instruction ahead, and after that SVC or software interrupt or supervisor call is executed, by which we can see the hello world on the terminal output of this schema process. After stepping 2 times ahead, the R7 is loaded with exit syscall, R0 is loaded with the exit status, and after specifying the SVC, the debugger session will be closed, the process will be closed, and the process will exit successfully with the exit status of 11, which we have declared in the program. So many of you can have a query like why you have not introduced the instructions concept earlier this video. The main reason or the main intention which I have is to provide a template, is to provide confidence or hands-on experience for creating an ARM binary, because just doing theory will just cost you nothing. Doing some kind of practical things will just help you out in understanding something. So that was the only reason by which I created these 2 videos earlier than those instructions and CPSR video. So the next video will be of CPSR and instruction, so don't worry. If you have any query related to this video, you can just ask in the comment section. You can download all the slides used in this video from the description below. Drop some likes and subscribe. You can follow me on Twitter and GitHub. That's all for this video. Meet you in the next one.